Right, hello, this is going to be a little walkthrough of the Level 3 Mechanics paper, the 2024 past paper from the NCEA website. I'll put it on Google Classroom for us as well, but I'll try and go through and highlight where the achieved merit and excellence points are made up. Now, already I've started to annotate it. It's because I messed up my words on the first attempt of this, so I'll just quickly go through this. We're told that a solid steel ball bearing with a radius of 7mm and a mass of 11.2 grams is released from different heights on a steel track. It rolls down and then travels over a series of bumps. Each bump and dip has a radius of 35mm. So up here, straight away, I've underlined the information I might need for an equation. And I've also just quickly converted those units because they're all in millimeters or grams, and we want everything in meters and kilograms. So for each one, by coincidence, I've had to divide each one by 1,000. So my radius of the ball is 0.007 meters. The radius of each curve is 0.035 meters, and the mass is 0.012 kilograms. Okay, we've got this handy little diagram here that shows on here the height h, which will probably be used later on, and then we've got the radius of each curve labelled as well. Question 1a. In one trial, the ball bearing reaches the bottom of the first dip with a velocity of 0.85 meters per second. Calculate the angular velocity of the ball bearing when it's at the bottom of the first dip, which is point x. So for A, we're looking at what the velocity of the ball is here. Now, if the ball is moving with a velocity, then its angular velocity doesn't depend on the curve, it depends on the radius of the ball itself. Because obviously this ball is rotating as it goes, because we are not told that it is a frictionless track, we are told it is a steel track. So it's indicating that we're actually going to be worried about its motion along the surface. From our equation sheet, we have that velocity is equal to the radius multiplied by the angular velocity omega. I've just written down my values from above as well, just to make sure they're super relevant and clear for me. But I want to rearrange this to get to angular velocity. Now, angular velocity is being multiplied by r. To undo that multiplied by r, I'm going to divide both sides by r. If I divide v by r, I just get v over r, and r divided by r becomes 1, leaving omega on its own. So now I've got an equation for omega using velocity and radius. I'll just substitute the values in, 0.85 divided by 0.007. So I'll go across to my calculator and just pop that in. And because I'm lazy, I'm going to skip the first naught, and I'll get an answer of 121. Oh, you can't even see the calculator, right? 121.4 meters per second squared. Didn't mean to do this all in red. Maybe we'll make the achieved questions red. So that's our angular velocity in radians per second. It seems like an awful lot, but if you've got a very small ball bearing moving at about a meter per second, it's got to do a lot of rotations to make it down that slope. Okay, but that's us. For part B, we are told to show that the maximum speed is 0.586 meters per second in order for the ball bearing to remain in contact with the track while going over the bump at point Y. The bump has a radius of 35 millimeters. Now, this is one of those questions where if we have something going over a bump or around a vertical loop, it's all to do with the normal reaction force. In this case, at the top of a bump or a lump, we have that the centripetal force Fc is equal to the weight, Fw for weight, minus Fr, which is the reaction force, which is what we are going to be looking at. But at the moment, at the maximum speed for it to be in contact with the track, that's going to be when the track is providing 0 newtons of force to keep the ball moving upwards. And so the only thing that's keeping it in that perfect motion is its motion. The reaction force will be 0. So at Vmax, Fr is equal to 0. So now my equation becomes Fc equals Fw. My centripetal force equals my weight. Now looking at the equation sheet, we have that mg, the weight force, must therefore be equal to the centripetal force, which is mv squared over r. Okay. Now we want to calculate the velocity, so we're going to rearrange this to get the v on its own, which is a little bit of a process. We're dividing both the right hand side by r, and that's the first thing we're going to get rid of. We're going to multiply both sides by r. If you multiply mg by r, you just get mgr. That is equal to mv squared. Now we've got our fractions out the way, it becomes a bit easier to deal with the rest. We've got m on both sides, and because it's on both sides, we can quite simply just divide through by m on the left and right, leaving us with gr is equal to v squared. We want v on its own, so we're going to square root the entirety of both sides, which gives us v equals square root of gr. I've just switched which way around they are, just because we are trying to calculate v, and that's normally how we write these sorts of things. Once we're at this stage, we just substitute our values in, where g from our equation sheet is 9.81, and this time, because we are analysing the curve itself, we are going to use the radius of the curve, which I'd already converted at the top of my page to 0.035, and my square root isn't quite long enough. But then I can just pop that into a calculator and get my answer of 0.5859, which rounds up to 0.586 meters per second. But it's always good practice, to put the unrounded number in first, forgetting my own advice, for 0.58596 from my calculator, 596, then that equals 0.586. Just to make it crystal clear that you have calculated and you're not just writing the right answer and hoping they don't notice you've done this bit wrong. But easy as that. And I've got my units added. Okay, so now we're on to question C, or part C. We are told to compare the forces acting at the top, which was point Y on that diagram, and the bottom, which is point X of that diagram as well, just here. And we're going to explain how the net force varies in these positions. Labelled force diagrams will be useful in supporting your answer, which is code for try and draw labelled force diagrams. They should really help you explain what you're saying. So we're going to start with two different diagrams. I'm going to draw them separately, even though they are very close to each other on here. You could just label this yourself, but I want to do it here to make it even bigger, give myself even more space. So down here we'll have point X, and over here we'll have point Y. Okay, so in each case we're imagining the ball is sitting right in the bottom of the pit here, and on the apex of the curve for part Y. Now, in position X, the weight is acting downwards because gravity always acts downwards. So I've got my FW labelled straight away. And gravity doesn't go anywhere if you're on top of a hill, and so an arrow roughly the same size as the first one, labelled FW again. Now here, the centripetal force, the net force acting on the ball, is towards the centre of this circle. If this is the outer edge of a circle, the centre of the circle is up here. The ball is being accelerated towards the centre of this circle with radius 35 mm from the previous part. And so we have our reaction force up here, and the reaction force must be larger than the weight force. Otherwise the ball wouldn't turn upwards through the curve at all. And so the reaction force goes here. On this side, this time, the reaction force is or cannot act downwards, it must still be acting upwards. And in order for the weight force to provide the centripetal force, which is what it's doing here, because here the circle is, the centre of the circle would be towards here, towards this point. The weight is the thing providing the centripetal force, and the reaction force will be a bit smaller than the weight force. Otherwise, again, the ball wouldn't turn the corner, it would just go up in a straight line, or in an upwards trajectory of some sort. Okay, so now we've got our two labelled diagrams. They're going to help us to write equations for the net force and the centripetal force themselves. So, we're going to just quickly say that the F net for position X here, I'm going to do it underneath position X here, we're going to say that the centripetal force, which is equal to the net force, is Fr, the reaction force, take away the weight force here. Okay? In position Y, we have F net is equal to centripetal force, and this time it's the weight force that's providing the correct directionality for the centripetal force. So it's going to be our F weight subtracted by the reaction force. Okay? Now, because this is meant to be a discussion, a comparison, and an explanation, we do have to give some words to go along with this. I've not left myself much space, but because my diagrams are there, essentially, I don't have to write too much. Okay, so we'll say, at position X, I'll try and keep it brief, you might want to use full sentences. At position X, F, the reaction force, acts towards the circle centre, and weight opposes it. I'm going to try and cram it in at one line here. And weight opposes it. At position Y, it's the other way around. At position Y, Fw acts towards the centre of the circle centre, and the reaction force opposes it again. Now, if you do have a look at the marking schedule, for achieve, you have to essentially provide any one of these statements. If you're not going to draw a diagram in the way I have and label them, you have to have said that Fr, the reaction force, is acting towards the centre of the circle and will be greater in magnitude than the weight force in order to provide the centripetal force. Because I've got my diagram here showing that with differently sized arrows, I do not need to do so. Over on the Y position, again, same idea. If you don't have a diagram, you have to say explicitly that weight will act downwards towards the centre of the circle and will be greater in magnitude than the reaction force. Therefore, the centripetal force will be equal to the difference between the two, weight minus reaction force. And here as well. For merit, you have to do an explanation or a diagram with some description for one position. For excellence, you need to fully describe both, just as done so here. Part D. This time we're going to energy. By considering energy changes, calculate the maximum height. Calculate the maximum height of By considering energy changes, calculate the maximum height. My laptop just ran out of battery. Above the top of the first bump, point Y that the ball bearing can be initially released from if it is to remain in contact with the track as it travels over the bumps. The ball bearing is a solid sphere and has a rotational inertia given by I is equal to 2/5 of mr squared. So, we're going to use an equation that involves the rotational inertia, and we will have to calculate that rotational inertia for our ball. Okay? Now, if we're going from position, from the top of the slope, over here, the top of the slope, to the top of point Y, we're going to have a change in energy. At the top of the ramp, the ball has gravitational potential energy. By the time it has travelled down and across to the top of the first bump, it will have transformed that energy from potential energy into kinetic energy. But because this is a ball that is rotating, we're going to have two kinetic energies, the linear and the rotational kinetic energies. Now, our equation for GPE is mgh. The equation for linear kinetic energy is half mv squared, and our rotational kinetic energy is half I omega squared. Now, from this little bit of information here, we can add some more value or more algebra here. You do have a choice. You can just calculate the rotational inertia and then put that number, that value, into this equation. I'm not going to, and I'll show you why. If I continue another line, mgh equals half mv squared, but this time make the substitution. I have 1/2 multiplied by 2/5 m r squared omega squared. So it looks a bit horrible right now, but immediately we can start cancelling out common factors. M exists in all terms, so we can just cancel them out straight away, leaving us with a bit of a cleaner equation. GH is half v squared plus, I'm just going to combine these two fractions, 1 times 2 is 2, 2 times 5 is 10. 2/10 r squared omega squared. Okay? So now we're at this stage here. We have quite a complicated expression. We do know most of the values. Now we're told in the question that this is again the moment that it's the maximum height, therefore the maximum velocity the ball can have as it goes over the bump to remain in contact. So let's put it back into focus. Which means our omega we're not sure of, but we know we calculated the velocity that occurs in, and so we can use the equation v equals r omega, rearranged again to omega equals v over r, where our velocity is the velocity that we proved in part B, 0.586. So 0.586 goes on top, and the radius of our ball was 7 millimeters, which is 0.007 meters. So now we can put that into a calculator. 0.586 divided by 0.007 gives us 83.7 radians per second. Okay. So now, all we're going to do is throw all of our different values into this equation, and we'll get h at the end of it. So h is half v squared. Our v is this 0.586. Just super clear for us. Half 0.586 squared. I'm going to put that in brackets just to make it clear that it's only that being squared. Plus 2/10. We could simplify to 1/5, but we'll keep it. Just why not? Our radius is 0.07 squared, and our angular velocity is what we've just calculated up here as 83.7, and that is going to be squared as well. Don't forget that the whole thing is divided by g, which on Earth is 9.81, and then we get typing on our calculator 0.5 times 0.586 and make sure you're putting everything in brackets to make sure you're not squaring or multiplying the wrong numbers by the wrong amounts. divided by 9.81, and we get our height of 0.024500 meters, which we can round to 0.0245 meters. Now this question is another one where you can gain excellence on. In order to get excellence, you have to do all of the above to get to this point here, a height of 0.0245 meters. For achieve, you have to do one of the following. Either just demonstrate that you're using the idea of conservation of energy, so this equation here would do that. Then you can either just work out the individual kinetic energies, either for linear or rotational. I didn't do that because I was confident I could do it all the way through. But in this sort of question, if you're feeling really unsure on how to put it all together, but you know you are calculating kinetic energies, just stick with the kinetic energy linear equation. If the rotational inertia and angular velocity are causing some difficulties, work out the energy. For this question, just calculating one of those energies gets you the achieve. For merit, you have to basically do all of this, but you are allowed to make one mistake. The alternative is calculating both kinetic energies individually. And as I said, for excellence, it's all of the above to get to your height of 0.0245. Now, question 2. This is another question about rotational motion. We're told that a golf ball of mass 0.0460 kilograms is placed into a light cup. What that means is the cup will be weightless, or massless, should I say, and therefore have no effect due to weight. And that cup is attached to a flywheel with a diameter of 0.22 meters. It begins to accelerate downwards at a constant rate of 1.83 meters per second squared. So this is our acceleration, and that is an A, not the Greek letter alpha. Part A, is to show that the angular acceleration of the flywheel is 16.6 radians per second squared. We are given the linear acceleration or the translational acceleration, and so we know in combination with our diameter or radius, we can work out our angular acceleration. Now the equation for angular acceleration is A is equal to R lots of alpha, which is this little symbol here. We want to work out alpha, and so I'm going to rearrange this equation by dividing both sides by radius to give us A over R equals alpha. Now, you're not going to lose marks for drawing untidy alphas, but I'm going to make it really crystal clear for your own sake, as well as the markers, that this is not an A. And for me, that means giving it extra flair on the upwards bit here, which is what an A in our alphabet does not contain. And now we've got our equation, we can just substitute our values in. Alpha is equal to A, which was 1.83, divided by the radius. We have a diameter up here of 0.22 meters, so our radius is just half that. So radius is equal to 0.110 meters. So here, for our radius, we're going to use 0.11 down here. And again, throw it in a calculator, and hopefully we will get the answer of 16.6. Oops. And I get 16.63 recurring, which if we round it, gives us 16.6 radians per second squared. As again, it's to show that question, make sure you write out the full answer as it appears on your calculator, then the rounded answer that you're trying to prove is correct. That's an achieve question for the right answer. Part B. If the ball and cup start from rest and fall through a distance of 0.75 meters, calculate the final angular velocity of the flywheel. Now, we are told that the entire system falls by 0.75 meters. If it does so, that means that the wheel itself will have rotated through a distance of 0.75 meters. Therefore, to work out the angular displacement, we're going to use another one of our angular translational conversion equations. D is equal to r theta. If our goal is to work out the angular displacement so that we can use one of our rotational kinematic equations, I'll just prep this in advance here. We need to know what our theta is, what our angular displacement is. Therefore, we're going to substitute, or rearrange this, so that we're dividing both sides by r to get theta is d divided by r. Our distance here was 0.75 meters, and our radius is, as above, 0.11 meters. We put that in a calculator. And we get an answer of 6.81 recurring for our theta. And so we can just round that to 6.82, because the 8, when it repeats after the 1, will round the 1 up to 2. So now we have our angular displacement. We can throw that into our list of values here. Now we're interested in finding the final angular velocity, so I'm going to put a big question mark here straight away. We are told that the ball and cup start from rest, therefore our initial angular velocity will be 0 radians per second. So I should add my units as well. And as we've just worked out our angular acceleration above, we can put that in here like so. So we have three values, theta, omega I, and alpha, and we want to find omega f. So we're looking for an equation that contains those four quantities only. That will be the equation, very similarly to translational motion from last year. Omega f squared is equal to omega I squared plus 2 alpha theta. And because we are already looking for omega f, we haven't got to do much rearrangement, but I am going to square root both sides in advance, just so that I'm left with omega f is equal to the square root of everything inside omega I squared plus 2 alpha theta. And now I substitute all my values in. I'm going to give myself lots of space for my square root. Omega I is 0. 0 squared is 0. Plus 2 lots of alpha times theta. So I'm going to put it in brackets just to keep it nice and tidy. 2 times alpha, 16.6, times theta, 6.82. Close the brackets, it's in the square root. And so I just type that into a calculator. 2 times 16.6 times 6.82. To give myself an answer of 15.05, which rounds up to 15.1 radians per second. Now for this question, merit is achievable in this. To do so, you have to calculate the final answer. For achieve, you have to either work out the angular displacement correctly, and so if you get a question with distances and radii, especially with pulley sort of systems, it's always a good bet to do that straight away. And the other ways you can get achieve are to work out, is to follow through the calculations if you make a mistake in your calculation of theta. So if you did this conversion wrong, or if you didn't do it at all, and used a different value of theta here, and got a different answer for omega f, but did all of this bit correctly with the wrong numbers, then you can still get achieved there. For part C, we are told to calculate the rotational inertia of the flywheel. we are told to begin your answer by calculating the force that is causing the flywheel to accelerate. A free body force diagram may assist you in calculating the tension in the string. Okay, now we're on to part C. We are told to calculate the rotational inertia of the flywheel. Begin your answer by calculating the force that is causing the flywheel to accelerate. A free body force diagram may assist you in calculating the tension in the string. So just quickly here, I'm just adding a couple of labels to my diagram. My weight force is the thing that's pulling the entire, or starting the entire movement, but this force is being applied to the string here. And so the string itself is experiencing tension, which is what is pulling directly onto the flywheel. And so tension is our force that we're looking for here. Or is the force that we're looking for here, yes. Now for this, because we are talking about a rotating flywheel, we're going to think about torques. Because this is an unbalanced system that's accelerating, we're allowed to use our torques, because torques are what cause things to accelerate when they are unbalanced. So when there is a resultant torque acting on the system. Now, the force required to turn this wheel is the difference between the force we would expect it to feel if there wasn't a wheel and the force it is actually experiencing. Now, the force that we would expect it to feel if this flywheel was had zero resistance to being turned, so had a zero rotational inertia, an impossible system, but we would expect the force to be weight, Fw. However, the actual acceleration we've calculated was not equal to 9.81. Over earlier in the question, up here, we are told that the acceleration is 1.83, which is a lot smaller than gravity's acceleration. So we know that this flywheel is giving quite a significant bit of resistance. To find the force that's causing that difference, we just find the difference in the two forces. So the weight force is the ideal world one, but we subtract what we think is the actual force that's accelerating it. I'm going to leave that as just as F, because it's just the force that is actually experienced. Now, if we change those into their equation forms, the force due to gravity is mg. Weight is mg. The force that is actually being experienced can be found by combining the mass and the acceleration. Newton's second law. If we know the acceleration and we know the mass of the object, then we can use Newton's second law, which says that a force is proportional to the acceleration if mass is the constant of proportionality. Okay, so our resultant force that we're experiencing, or the force that's been required to turn the flywheel, is mg minus ma. I'm going to go over to the other side of the paper and I'll add those bits in. So, if we know that our F is equal to the weight minus Newton's second law's force, then we can start adding these into our equation. If we substitute F into the F here, we get tau is equal to mg minus ma all multiplied by d. I'm going to use brackets here to make it nice and clear. And then we can just start substituting values in. The mass of the ball, I have no idea what that was 0.046 for our golf ball. So 0.046 g, which is 9.81, minus our mass again, 0.046, and then our acceleration was 1.83. Okay. Now the distance in our equation here is the distance that the force is acting from the centre of rotation. In this case it was d, and we are told that that radius, or that radius, was 0.11 metres from the very start of the question. So again, you've got to dig all the way back a page to the top to find that necessary information. And a little trick, if you're finding that you've got lots of brackets together, if you're done adding little brackets, I use square brackets for the entire equation like that. Multiplying it by d, 0.11, and then we can start typing that into a calculator. Again, being careful of where you're setting your brackets out to make sure that everything that should be multiplied is multiplied and those that shouldn't aren't. Times 0.11. And we get 0.0403788. So our torque is equal to 0.0403788. And again, because it's a torque, in Newton meters, not equals Newton meters, sorry. That's our unit. Now we didn't want to find the torque, we wanted to find the rotational inertia. So using our second torque equation, we have tau is equal to I alpha. Our alpha is what we calculated in part 1, or part A, sorry, as 16.6. And so we're going to do alpha is equal to tau divided by I. Just a simple rearrangement to get alpha on its own. We've just worked out torque as 0.0403788 divided by, I forgot what it was already, 16.6. And if you've left your answer in your calculator, it saves a bit of typing to get 0.00243 kilogram meters squared. If you sort of do remember the rough equation for, or one of the equations for rotational inertia, we've got mass multiplied by radius squared, so the units are kilogram meters squared. Now this was an excellence question. If you did all of that and got this final answer, that was excellence. If you made one error in your calculations, then that takes you down to a merit. To achieve, you had to, first of all, identify tension as being the force that's turning the wheel, and then use either this torque equation or this torque equation. It doesn't give any specificity with regards to how you use those two equations. You just have to have demonstrated and tried to use a torque equation for achieve there. Okay? Part D. Explain what will happen to the final velocity of the ball and cup if the flywheel is replaced with a solid disc of the same radius and mass as that of the flywheel. Now, while we are given no equation for our rotational inertia, we do know that rotational inertia is proportional to mass r squared. This is not an alpha, this is a proportionality symbol, very similar, but they are different. Now, if we look at the diagram here, it's quite obvious what's happened. We've now got a solid metal flywheel, as opposed to here, where the spokes meant there were lots of air gaps in the flywheel. And as in any discussion like this, it's always important to say what will stay the same, and therefore what will change. So, if we're saying, as we're told, that the radius is the same and the mass is the same, then we know that if mass and radius remain constant, the distribution of that mass must have changed. Because in the flywheel, if it's the same mass as the solid disk in part D, part D, this metal must be more dense than the new solid disk, because there's a much smaller area here that is taken up by the flywheel itself. Therefore, if the mass and radius are the same, the mass distribution must have changed. And again, if we flick back to the previous diagram of the flywheel, we can see that there's a lot of empty spaces nearest the centre of rotation. A lot of the mass is concentrated on this outer rim, whereas in the new flywheel, solid disk, those areas nearer the centre of rotation are filled in. Therefore, the mass is being pulled inwards from that outer rim to be more compact. The mass distribution has become, or has moved closer to the centre of rotation, if that happens, just like when we saw with figure skaters, if you compact the mass distribution, if you bring yourselves in tightly, then your rotational inertia decreases. Remember, the bigger your mass distribution, or the more mass is distributed more widely, the greater your I. If mass and radius increase, your I gets bigger. But if you are compacting the system, then your I is getting smaller. The mass distribution has moved closer to the centre of rotation, therefore the rotational inertia will have decreased. Okay, now this is where we start to link in our various equations, and because we're talking about final velocity, this is going to take quite a few equations to make that point. So, we want an equation that's going to link acceleration and rotational inertia. We have that, we used it just in the previous part. Oh, sorry, it wasn't actually on the screen. So that tau is equal to I alpha, as tau equals I alpha, if our rotational inertia is decreasing, we therefore have to have an increase in angular acceleration because the size of the torque is unchanged. The torque was provided by the golf ball in the cup, and as the radius is the same, we've already said so, therefore the only thing that must change is the angular acceleration. So if tau is staying the same, and we've just said our rotational inertia decreases, then our angular acceleration must increase. As tau equals I alpha, angular acceleration must increase. Okay? Now, because the angular acceleration isn't what we're not asked to discuss the angular motion, we're talking about translational final velocity, otherwise it would have said angular velocity. If you ever see just velocity on its own, it's referring to translational velocity. If our angular acceleration is increasing, then we can link that to our translational motion with the following equation. Acceleration equals R alpha. Because the radius is staying the same, and we've just said that our angular acceleration is increasing, it means our translational acceleration must increase. So we can say, as a equals r alpha, the translational acceleration will increase. Then a final, therefore, if the flywheel experiences a larger acceleration, which we've just proved it will have an increased final velocity when replaced with the solid disk. Just to tie it into the question, like that. Sorry. So, this is another excellence question. In order to achieve excellence, you have to have these various points. You can alternatively discuss this in terms of energy, but I think this is a lot more intuitive to just think of it as torques and rotations. For achieve, you have to state the fact that the rotational inertia decreases and therefore the final velocity increases. So if you can, the big point here therefore is that having a solid disk has a more compact mass distribution than a flywheel with spokes, therefore the rotational inertia I gets smaller. For merit, you had to then discuss the mass distribution to the rotational inertia, or the rotational inertia's change, the decrease, to the increased angular acceleration here. So for merit, you had to either do this sort of paragraph here, or this equation and sentence here. For excellence, all of the above, although you could go down the road of energy and prove it that way. Okay, final part. Question 3. Simple harmonic motion. A ball bearing is released on a watch glass and rolls back and forth with simple harmonic motion. The watch glass is a shallow, semicircular glass bowl with a radius of curvature r. Now this is one of those questions that's purely recall based. I'm going to do 2 bullet points, both of which are going to discuss the restoring force. First of all, the restoring force. In this case, that restoring force will be gravity because it's a marble rolling up and down a hill. The restoring force must act towards the equilibrium point, point 1. And the second one is that the restoring force, or the size of the restoring force, is proportional to the displacement. And I've run out of space. You shouldn't go into these gaps, but I am. Good. Nice and easy. So that's an achieve question because it is just recall. You can write this mathematically. Alternatively, the way you would do that is that because force and acceleration are related, are proportional, we can say that the acceleration is proportional to y squared. The reason it's negative, not squared, I don't know why I squared it, sorry. The reason it's negative is because if the ball is up to the left, if its displacement is to the left, then the acceleration will be acting to the right, in the opposite direction. And that's always the case. If the ball's up here, suddenly the acceleration will be the opposite direction. Again, opposite the displacement, yes. Now the size of the restoring force is proportional. You can just say that F R is proportional to minus y again. Okay, So both of those little summary statements do the trick, but I would always stick with the sentences just because the negative signs are very easy to miss. Part B. The ball bearing is released from 0.04 meters from the right of the equilibrium position and oscillates with a time period of 0.882 seconds. Using reference circles or otherwise, calculate the displacement of the ball bearing after 1.2 seconds. Now again, as we've said, the reference circles, in my opinion, just add more layers of complexity to these sorts of problems. I think it's far easier for us to jump straight in to the equation sheet for displacement. Because we are starting from a displacement, this will be our amplitude. If we're releasing it from that height, that's the maximum distance from the equilibrium point that it will reach. It cannot go further without taking in extra energy from somewhere. And so this is our amplitude. And we have our time period stated here. So the equation for displacement is y equals a cos omega t. And it's a cosine, not the sine set, because we're starting off displaced, and cosine begins its graph with a position of 1. Somewhat like that. Okay, it starts off at a maximum, which is what we want. Now, we are told the time period, which doesn't appear in this equation. But remember that omega is equal to 2 pi f, where f itself is equal to 1 divided by t. Sorry, down here. Omega is 2 pi f, and f is 1 divided by time period. So we can work out the frequency from our time period, or just make the change that omega is 2 pi over t. Then we're going to substitute our values in to this equation. 2 pi t over capital T, remembering that little t is the time that has elapsed and big T is our time period. Our amplitude from the question was 0.04. Cosine of 2 pi, the time that has elapsed was 1.2 seconds, and our time period was 0.882. Making sure our calculator is in radians, because we're talking about angular velocity, and 2 pi is the radian measurement for a circle. We're going to do 0.04 times cosine of 2 pi times 1.2, all divided by 0.882, close the brackets, and so we get our displacement of minus 0.0256021 meters, which we will round nicely to minus 0.0256 meters. You've got a negative here, which is okay, because it just means it's gone to the opposite side that it was started on. Okay? Now, using your reference circle, if we're starting at this position always, because that's where the positive x-axis is, our time period is 0.882, which means to do an entire lap of the circle will take 0.882 seconds. So our 0 and 0.882 are at the same position. Just by doing some quick halving, the halfway point will be 0.441, therefore our quarter points will be 0.2205, I guess, and 0.6615. So now we can check our answer if it makes sense or not by seeing where our time of 1.2 will take us. So if we do one lap, that's 0.882 seconds taken up. The extra sorry for doing that yelling on the street. The bit extra is 0.318 seconds, which will take us over this quarter and over here, somewhere between 0.22 and 0.44. Our 0.318 goes. In this case, our value is negative. It's on the negative side of the graph, which is what we got here. Perfect. Part C. We are told that eventually the ball bearing comes to rest. Using the axes provided, draw a labelled graph of the displacement versus time for 5 complete oscillations. Include values for displacement and time. Now, it's a bit of a misleading instruction here to include values for displacement and time. Really, what you can get away with is your time period here of 0.882, and then you're just going to multiply that up each time. So 0.882 times 2 is 1.764. If you times it by 3 instead to find the third square, 2.646. Times it by 4 to get the fourth square, 3.528. And then our final one, we want 5 complete oscillations of 4.41. And obviously we're starting at 0, so it'd be good to include that. We'll put t, measured in seconds, on the x-axis, and then we'll talk about our amplitude, or our displacement, sorry. So our displacement's going up here, it's going to be y, which is our symbol for displacement, measured in meters. The biggest possible value we have is 0.4, because that was our amplitude from before. So we can put a 0 here for the halfway point, the equilibrium position, and minus 0.4 meters here as well. Now before I go any further, I should just explain, with my x-coordinates, they are horrible numbers, and normally when we're drawing graphs, we would never ever do this. However, we've only got 6 squares, and it's unlikely you're going to find a scale that's easy to work with. And because the whole idea of this is it's not a precise graph, it is essentially just a sketched graph. It doesn't say that, but we're just estimating the shape of our graph, really. It doesn't matter what this is. What I want is each of my complete waves or oscillations to occur at one of these bold lines. Now, we know this is going to be damped because, sorry, let me start again. We're starting at 0.4 meters. It's a cosine graph. So our first starting position is going to be right on the y-axis at the amplitude. Now, because we're told that there is damping, that the system is losing energy, each time we start a new wave cycle at each of our multiples of time period, we're going to just draw a little dot just a little bit shorter than it was before. There's no set amount you have to decrease it by, other than the fact it is decreasing each step. And try and make it a nice smooth curve, and whatever you do on the top, you are going to roughly do at the bottom when you get to do your envelope, damping envelope or oscillation envelope, after you've drawn your sine curves or cosine curves, as this one will be. So I'm just going to very gently add some dots, gentle enough I can rub them out if I've changed my mind. But now, this is the important bit. These dots at the bottom we're going to ignore, because we're starting at amplitude. Each wave cycle should start at the amplitude. So with your cosine graph, it's going to be very narrow in this graph paper, but you've got to go down to the bottom of this envelope that we've just sort of shaped up for ourselves here. And if you're really keen or worried, you can start actually drawing those dotted lines in, just to give you your space with which to work. Okay, so you might as well do it for the top as well, just to give you sort of guidance when you're drawing your curve, because if you're like me, these cosine curves can have some pretty wild shapes. Okay, so when we're drawing our cosine curve, we're keeping it within these 2 dotted lines, and it is narrowing, which is what we want for damping. So we're starting at amplitude, we're going to bring the line down quite steeply until we touch that dotted line, then shoot back up until we get to another new amplitude, a slightly smaller amplitude here, and we turn the curve around, go all the way down again, bring it back up to the newer amplitude, which is a bit smaller than before, and we're just going to do this for the rest of the curve. Now, I didn't tell you I did, but I'm sure you saw I've changed to a pencil because my drawing, I'm really not liking it, but it is doing the job. If you do it in pen and make a mess of this, there will be a spare bit of graph paper at the back of the exam for you to use. Make sure this time you do use a pencil. But this sort of graph here would be perfect. Now, you don't have to do your envelope as wide as I've left it. You can do yours getting narrower much quicker. But the key marking points here for merit is to have all of the above that I'm going to talk about. But the 3 achieve points, to get achieve you only have to have one of them. The idea that this overall shape is getting smaller. It is decaying, it's getting smaller. That's one marking point. If you have any graph that tapers off symmetrically, then that's an achieve. If your y value starts at amplitude of 0.4, that's another way to just get achieve. And if your time period has constant jumps, which any system does, even when damped, that is another way to get achieved. For merit, you have to have the amplitude here, you have to have constant time period jumps, and you have to have a decreasing width of your envelope. Okay? So now we're on to the final question, where we're going to explain everything I have just said. This is an excellent answer. And so we are going to go into some detail here. We are going to include some equations to justify our answer. So, the big thing to say, first of all, is that initially, because the ball bearing's starting raised up at amplitude, it has initially got gravitational potential energy. Initially, the ball bearing has gravitational potential energy, which, if you're writing questions about gravitational potential energy, write it out first in full, in brackets, put GPE next to it, so that the next time you want to write this out, you can just write GPE and not have to write the whole thing. This is how abbreviations should work. You should always write it out in full first, with the abbreviation in brackets afterwards, then you can use the abbreviation as required. Okay, so initially the ball bearing has gravitational potential energy. Because this is a damping question, we are losing energy in the system, and so we're going to be only interested in energy transfers and where that energy is going. As the ball starts to roll, GPE is converted to kinetic energy as the ball begins oscillating. So again, I'm being crystal clear with what's occurring and when. I'm going to give a general equation here. So at any point, the E total, the total energy of the system, is equal to EGPE, using my abbreviation, plus EK, kinetic energy. Now, because we are not told that this is a frictionless surface or an icy surface, and we are told that it's made of glass, we can assume there is friction. And obviously, because it's damped, we know there must be some sort of resistive force. So, as the ball rolls back and forwards, or back and forth, some kinetic energy is lost due to friction Now you could also give air resistance as an example, but air resistance is essentially the friction between air and object. So friction covers air resistance now. So some kinetic energy is lost due to friction, so the total energy of the ball decreases over time. Which is what we've said in our graph up here. Because the oscillations are decreasing in amplitude, we have less kinetic energy being converted into gravitational potential energy, and so the ball is unable to go as high up the side or up each side of the watch glass. And so our final sort of sentence will be as follows. I have no idea if that was on the screen this entire time. If it's not, I'm sorry, I'll leave it here so you can pause it and have a look. My mistake. But our final sentence is going to say a decrease in the total energy means that the maximum height reached by the ball will decrease. Not decreases. A decrease in total energy means that the maximum height reached by the ball will decrease as there is less energy to be converted into GPE. Now, it's important, we've done an excellent description here, but we are told to name this phenomenon, and we haven't done so in this answer. I've said it, but I haven't written it. And so, just quickly, this is called damping. Now, this is an excellence question, as I said. Making all these points is needed for excellence. In order to get merit, you have to make this statement here. This is called damping. In addition to naming this process, or this phenomenon, you have to state that either we are losing kinetic energy due to friction, or the fact that we have less total energy will cause less gravitational potential energy. For achieve, we just have to say that energy is lost due to friction, the amplitude decreases, or the maximum height reached decreases. That's what displacement is in this case, it is the maximum height by the ball, or just naming this damping. So if you have no idea how to describe all this, but you know this is damping, just saying this is damping gets you the achieve credit. For merit, you've got to link the energy to the cause, or the energy loss, sorry, to the cause, or the decrease in gravitational potential energy as a result of losing kinetic energy. Altogether, we have our excellent answer.